Good morning, honorable speakers, distinguished guests, ladies and gentlemen. Welcome to the seminar series of International Seminar Chemical Engineering Suhadi Reksawardoyo, known as STKSR, in conjunction with Symposium on Photocatalysis and Photocatalysis, known as Symphosis. Today's webinar's theme is Challenges and Future Outlook of Photocatalysis Technology. Let me introduce myself. I am Fatur, student from the Department of Chemical Engineering, Institut Teknologi Bandung. It is a great and valuable chance for me to be your master ceremonies for today's event. On behalf of 2020 STKSR-Symphosis Committee, I would like to extend a very warm welcome to all of you. We appreciate you taking off your busy schedules to join us today. This webinar series is supported by the ITB Chemical Engineering Alumni Association, Badan Kejuruan Kimia Persatuan Insinyur Indonesia, and the ITB Chemical Engineering Student Association. And also, this webinar series is a series of pre-events from the 2020 STKSR-Symphosis activity organized by the Department of Chemical Engineering, Faculty of Industrial Technology, Institut Teknologi Bandung, with the theme of Circular Economy for a Better World. Now, I would like to start this event with the national anthem, Indonesia Raya. Ladies and gentlemen, please rise. Ladies and gentlemen, please be seated. Next, I will convey the health and safety regulations in this pandemic condition. If you're outside the house, then 1. Participant must use masks and other personal protective equipment. 2. Participants must keep a distance of at least 1 meter from other people. Then I will read the rules of conduct during the event. 1. Participants are not allowed to turn on the mic and camera during the event. 2. Participants are only allowed to ask questions through the chat room in Zoom or YouTube from the beginning of material presentations by speakers until the end of questions and answer session. 3. Participants are mandatory to fill in attendance form correctly through the link that will be provided in the chat room in Zoom and YouTube during the webinar. The data will be used to send e-certificates for those who previously registered. Now, we are pleased to have an opening speech from Mr. Professor Brian Yuliarto, the head of Faculty of Industrial Technology, Institut Teknologi Bandung. Professor Brian, the time is yours.
Okay, thank you. Sorry, I cannot open my video. Is it enough? Only my voice or? Hello? Sorry, I cannot start my video. Okay. Thank you. Okay, thank you very much for my time. It is a great pleasure for me, especially to declare open the International Seminar on Chemical Engineering Suhadi Reksawardoyo 2020. As we know that Professor Suhadi Reksawardoyo is actually our previous Ministry of Research and Technology in previous time, long time ago, and we make this dedicated meeting so that we can remember his previous work for the development of the chemical engineering in Indonesia, especially, and also research and technology in Indonesia. This international conference is also in conjunction with the symposium on photocatalysis and photocatalysis 2020. And of course, we welcome the participants from all over the world who come here through online to exchange experience and work and share together a few days on the exciting field of chemical engineering, and more special on photocatalysis and photocatalysis. I first wish to extend to you the greetings of the board of Faculty of Industrial Technology at Institut Teknologi Bandung, where the chemical engineering department, which consists of some undergraduate programs and as well as graduate programs, belong to the Faculty of Industrial Technology. I wish to thank, of course, to Professor Chandra Setiadi, the head of official committee, for his efforts to prepare this great conference together with all teams and members. We have the privilege of holding this conference in this beautiful ITB campus in Bandung City. It should be like that, but however, this pandemic forced us to keep our distance while hold this conference. So I imagine that we can going together in our big meeting hall at ITB. It is very beautiful and very nice city of Bandung. Fortunately, we cancel and we prepare it in online. I hope this condition not decrease our spirit to share and to grow the knowledge during this conference. In these times, calling for the challenges and future outlooks of photocatalysis technology, I believe this field is very important for our life and our industry especially. So we really hope that this meeting can share and the experience as well as the knowledge. So the result will be much better for our technology, our science, and of course, we hope some collaboration also yielded in this conference. Before closing, I have to extend further thanks to all supporters for this conference, especially Indonesian Photocatalysis Associations, and also my friend Pak Agus Saryono for coming this conference, and some other speaker. I think also we have here Dr. Wibawa Hendra Saputra from Chemical Engineering ITB, and also we have great speaker from Japan, Daikin Japan, Dr. Yoshio Okamoto, and also Professor Nurul Taufikur Rahman. This is, I think, also my long time ago we met in Japan together while we are doing our study. Of course, we also believe that there are some condition that we cannot doing the conference as well as like we meet directly in the building, in the room, and we share directly. We have a dinner, and we have traveling together. But we believe that let's make it as much as our efforts, so we can make this meeting very productive, and finally we get the development much better in our country. Of course, we also finally thanks to all supporters. I cannot list it one by one, and let's make you happy to enjoy this conference. Thank you very much.
Thank you, Professor Brian, for that wonderful speech. Now, continuing the following agenda, we are pleased to have an opening remark from Dr. Agus Haryono, the Deputy for Engineering Science from Indonesia Institute of Science. Mr. Agus, the time is yours.
Thank you. Thank you very much. And good morning, ladies and gentlemen. It is my pleasure to welcome you, all of the participants for this event, the seminar or symposium on photocatalysis and photocatalysis. And I also happy because Professor Brian has mentioned me that Professor Brian is a long time friend. Even I stay in the same apartment, yeah, during my stay in scuba, during I stay in postdoc in ice scuba.
Nice to meet you.
And I also would like to thank to all of the speakers, Professor Nurul Taufikur Rahman from Research Center for Metallurgy and Materiality, Dr. Wibawa Hendra Saputra from Department of Chemical Engineering, ITB, and also the participant from Japan, speaker from Japan, Dr. Yoshio Okamoto from Daikin Industry. And all of the speakers will speak on their perspective and how to develop photocatalysis for several applications and how to deliver the result of photocatalysis to the industry. And I believe that the application of the photocatalysis is very broad, and the research on the photocatalysis will become very active. Even in Indonesia, many researchers are doing research on photocatalysis, and some of them they have applied also in industry. And one of the speaker will be mention the application of the photocatalysis for environment. Actually, in LIPI, we also develop many applications of photocatalysis. One of the new activity on the photocatalysis is the application for the pharmacy, and many kind of the application will be I think Professor Nurul or also Dr. Okamoto from Japan, because he also representative from the industry association for photocatalysis in Japan. I believe that they have many example for the application of the photocatalysis. And I also like to thank that LIPI has been invited to join as the co-host for this symposium as the pre-event for STKSR. That I'm very happy because Dr. Osi from LIPI is also very active researcher. She also graduated from ITB, and she continuing his research for PhD and postdoc in Japan, and she is very active for research on photocatalysis in LIPI, and I believe that the result of her research will be very important in this event. And I also invite all of you to have a possible collaboration between LIPI and a researcher in Indonesia. And as Professor Dian mentioned before, that during the pandemic, the symposium cannot be in the symposium hall or symposium room, but I believe that this condition will not decrease our enthusiasm, and I think the participant for this seminar is can be increased, yeah, if the symposium held offline, the member of the attendance for this symposium will be only for Indonesian, but I think because this is virtually or conducted by online, the participant will be not only from ITB, from LIPI, or from surrounding areas, but also from all of Indonesian area, from even from overseas can join this symposium. Before I closing my statement, I'd like to again thanks to organizing committee, steering committee of this symposium, and I hope all of you can enjoy this meeting. You can communicate each other during the symposium in the Photocatalyst Association Indonesia. I hope the Photocatalyst Association Indonesia will be grow and can exchange their experience during the research activity on photocatalysis, and hopefully they can deliver the research to the industry, as some of the speakers will be deliver their experience, how they deliver the research to the industry. Thank you very much for your kind attention. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam. Thank you, Mr. Agus, for that wonderful remarks. I also hope that LIPI and ITB can have many collaborations in the future. Now, I will introduce the profile of today's webinar's moderator. Today's webinar series will be moderated by Mr. Dr. Engineer Aditya Farhan Arif. Mr. Arif is a manager of new investment from PT Rekayasa Industri. Now, without any further ado, I would like to invite Mr. Arif to begin the main session of this event. Mr. Arif, the time is yours.
Okay, thank you very much. Honorable speakers, ladies and gentlemen, good morning. Welcome to the webinar on the challenges and future outlook at photocatalytic technology. And as introduced earlier by the Master of Ceremony, my name is Aditya Arif, and I'm serving as a moderator for today's webinar. Ladies and gentlemen, a photocatalyst is a catalyst which is active under a certain wavelength of light. It offers a solution to the need for sustainable energy and environment. It takes a full advantage of the light as the free energy to improve the environmental quality, for example, by removing organic pollutant, reducing CO2, as well as to provide renewable energy and value-added chemicals. In this webinar session, from the three speakers, we will elaborate the development of this technology. We will also learn how Japan developed this technology and standard, any required standard, and how to put nanotechnology, including photocatalysts, into production in Indonesia. So without further ado, let me introduce the first presenter, Dr. Wibawa Hendra Saputra, or commonly addressed as Hendra. Dr. Hendra is now serving as lecturer at the Department of Chemical Engineering ITB. He received his bachelor's from the Department of Chemistry at the Institute of Technology Bandung, Indonesia, and continued to the master's degree at the University of Twente, the Netherlands, where he started to focus on the research on photocatalysis. He received his PhD from the University of New South Wales, UNSW, Australia, and also did his postdoc at the same university. So, ladies and gentlemen, please welcome Dr. Hendra. Dr. Hendra, the room is yours. You have 20 minutes.
Okay, thank you, Dr. Adit, for the short introduction. So I will try to share my slide first before I start my presentations. Okay, I just want to make sure whether the slide is already appeared in your screen.
Yes, perfect.
Okay. Good morning to the distinguished head of the STKSR 2020 Official Committee, Professor Chandra Setiadi, and Dean of Faculty of Industrial Technology, Professor Brian Yuliarto, and to the honorable speakers, Dr. Yoshio Okamoto from Japan, and Professor Nurul Taufikur Rahman from LIPI, and all distinguished guests, committee, as well as audience. So my name is Wibawa Hendra Saputra, from Department of Chemical Engineering, Institute of Technology Bandung. So it is a great honor for me to be one of the speakers in pre-event STKSR 2020. So today I would like to give a presentation entitled Photocatalysis as Promising Technology for Energy Conversions and Environmental Remediations. So this is actually the outlines for today's presentations, which consists of short introductions, including my academic background and research focus, and research background, principle and mechanism of photocatalytic technology, research findings, future prospect of photocatalytic technology, and concluding remarks. Firstly, I would like to give a short introduction about my academic background and current research focus. So as explained by the moderator, Dr. Adit. So I did my bachelor degree in chemistry at Institute of Technology Bandung with a research topic on computational chemistry, and then continue with the double degree master programs consisting of 1 year in ITB and 1 year in University of Twente with the research topic about developing photocatalysts for wastewater treatment. And I did my doctoral degree at the University of New South Wales from 2014 until 2018 with a research topic on the utilizations of UV light as pre-treatment for organic oxidation. And I did my postdoc for 3 months at the same university with the same topic and supervisors. So my research is actually emphasized on developing two technologies, which are electrochemical and photochemicals for environmental remediations and energy conversions. So it consists of wastewater treatment, in particular dye and organic waste oxidations, CO2 reductions to value-added chemicals such as carbon monoxide, methanol, ethanol, ethylene, and so on. Water splitting to decompose water into hydrogen and oxygens, and the hydrogens actually can be utilized further on in several applications such as fuel cells and many other applications. And lastly is actually methane oxidations to methanol. So during my research in master and doctoral programs, so I already developed several catalysts, which is tin oxide-based catalyst, copper-based catalyst, carbon-based catalyst, and titanium dioxide-based photocatalyst. So what is the research background that makes me emphasize on developing photocatalytic technology in order to solve environmental problems and energy issue? So as we know that the increased industrial activity has created an undesirable chemical pollution in air, water, and soil. So nowadays, around 1.2 million tons with 10,000 different synthetic dyes and pigments are actually produced annually worldwide and used extensively in dye, textile, and printing industries. So it is estimated that about 10 until 15% are lost in industrial effluents, which causes environmental pollutions. So in addition, carbon dioxide emissions in Indonesia continue to increase every year. So for example, in 2018, carbon dioxide emissions were recorded to have reached 500 metric tons per year. And these emissions is actually mostly contributed by the industrial sector by around 30%, followed by the transportation sectors and electric generations. So as we all know that the carbon dioxide will have effect on the global warming. So according to WHO data in 2018, more than 95,000 people in Indonesia die every year due to CO2 pollutions. So which has an effect to the emergence of various chronic diseases. So then what is the solution in order to solve these environmental issues? So there are actually many technologies which have been developed in order to solve the environmental issues, such as wastewater and air pollutions or CO2 emissions, so such as membrane bioreactors, membrane nanofiltrations, reverse osmosis membrane, thermochemical, electrochemical, and photocatalysis. So photocatalytic technology is actually chosen due to its various advantages, including the first one is cost-effective technology due to its raw material is very abundant and cheap. Second, the technology is environmentally friendly since the conversions of the organic contaminants is form carbon dioxide and water in the case of wastewater treatment and value-added chemicals in the case of the CO2 reductions, such as formic acid, methanol, ethanol, ethylene, and so on. Third, this technology provides energy saving since this technology is operated under ambient conditions, so at room temperature and atmospheric pressure, initiated by only UV and visible lights in order to perform the reactions. And fourth, this technology provides the sustainable technology. So since the technology use catalysts and sunlight, which can be used sustainably. So these figures is actually provides or some examples in Europe, so which already applied the photocatalytic technology in various applications. So for example, in Saarland, Germany, they already provide or generate the wastewater treatment plant using the photocatalytic technology, and in Rome, Italy, and Brussels, Belgium, so they already applied the photocatalytic technology for air purification. So so the catalyst is actually doped in the buildings as well as in the tunnel in order to purify the air pollutions. So in order to implement photocatalytic technology, sunlight, as we know that using sunlight as one of the driving force, so it's also support in the term of the sustainability of this technology. So as we know, the solar energy is the most abundant energy resource on Earth up to now with around 0.173 million terawatt per year. So, and Indonesia is actually receives 3.6 until 6 kilowatt hour per meter square per day of solar irradiation intensity, or equivalent to annual power output of around 1,500 kilowatt hour. So based on the figures on the top right corner, so it seems that the sunlight consists of 2% of UV light, 47% of the visible light, and 51% of the infrared. So then what is the principles and mechanism of the photocatalytic technology? So in principles, photocatalysis can be defined as the accelerations of reactions by using the catalyst and light as a driving force. So the material that commonly used for photocatalysis is semiconductors, since it has a band gap energy in the interval of 1.5 until 4 electron volt, while the insulators and conductors cannot be used due to its large band gap and the overlapping of the conduction band and valence band, respectively. So among the semiconductors catalysts, titanium dioxide, cerium oxide, zinc oxide, and carbon nitride are the most common used catalysts for several applications. But in these presentations, I will focus on the titanium dioxide-based catalyst. So in principle, briefly, the mechanism of the photocatalytic technology, first, light, whether it's UV light or visible light, is actually initiated to the semiconductor-based catalyst, which has an energy higher than the band gap of the energy of the semiconductor photocatalyst, irradiated, and it will stimulate the electron excitations from valence band to conduction band. So when the electron is actually excited to the conduction band, the electrons and holes will be perform the reductions and oxidations reactions. So for instance, in the case of the photocatalytic carbon dioxide reductions, the carbon dioxide is reduced in the conduction band to form or to generate the products such as formic acid, carbon monoxide, formaldehyde, methanol, methane, and so on. While in the valence band, water will be oxidized to generate the oxygens. In addition, in the case of the wastewater treatment or organic pollutant oxidations, so the electron and holes in here will provide or generate the reactive oxygen radicals. In this case, the oxygens will react with the electrons in the conduction band to generate superoxide radicals, while the holes in the valence bands will react with water in order to generate the radical or the hydroxyl radicals. So both radicals is actually very important key roles in order to degrade or oxidize the organic pollutants. So this actually several applications that can be used by using the photocatalytic technology. For example, wastewater treatment, bacteria removing, air purifications. In the case of the fuel productions, photocatalytic technology can be used for CO2 reductions, water splitting, methane oxidations, and so on. So among semiconductor catalysts, titanium dioxide is actually the most common catalyst that use, and also among the crystal phase. So they actually consist of 3 different crystal phase, which is anatase, rutile, and brookite. So the titanium dioxide anatase is actually the most active crystal phase compared with the rutile and the brookite phase. However, the titanium dioxide has limitations such as insufficient utilizations of the visible light due to the large band gap. So it's around 3.2 electron volts, the aggregations of the nanoparticles, and also the low adsorptions of the organic pollutants. So therefore, several strategies have been developed in order to increase the photocatalytic efficiency of titanium dioxide, such as doping with the metals on non-metals, surface modifications, Z-scheme heterojunctions, and also the defect generations. So my research is actually emphasized of creating the defect on the titanium dioxides, since the defects can actually decrease the band gap and hence make the titanium dioxide become visible light active. Based on the scheme in here, it can be seen that by introducing the defects into the titanium dioxide, it can actually lower the band gap energy of the titanium dioxide. So the visible light can be activated the titanium dioxide defect rich, in order to perform the redox reactions. So based on the constraints, I will focus with the strategy A and C, based on my research. So using a metal doping such as platinum, gold, and copper, and also generations of cation or anion defects. So my research during my master program, I did 2 methods in order to introduce defect sites in titanium dioxide catalyst. So the first method is just physical mixing of titanium dioxide with the titanium trioxide with the ratio of 1:1, and doing the calcinations from 300 until 900 degrees C for 3 hours. So it seems, interestingly, it seems that the colors is actually changing by increasing the calcination temperature from the grayish color become yellowish color, and finally at the higher temperatures, it will produce white color of the powders of the mixtures. So based on the X-ray diffractions, it can be seen that the anatase and rutile phase is actually generated by calcining at 600 degrees C and 900 degrees C. However, at 300 degrees C is only anatase phase. And based on the Raman spectroscopy, XPS, and EPR, it confirmed that the titanium 3+ defects is successfully generated in titanium dioxide. So based on the UV phase absorption spectra, it can be seen that the M600, or the mixtures that calcine at 600 degrees C, which is the yellowish powders, it gives the strong absorptions in the visible light regions. So based on the BET measurements, it can be seen also that by increasing the temperature of the calcinations, it decreases the surface area. And based on the morphology from SEM measurements, it can be seen that the appearing have fish skin-like structures in M600 samples can be seen, so which is incorporated of the titanium 3+ defects in the titanium dioxide photocatalysis. So the photocatalytic activity assessments is actually conducted in the lab scale using the home-built reactors. It's very simple, just using a beaker glass. There's a magnetic stirrer in here and also the UV lights, with the catalyst loading of 50 milligrams, and the methyl, the concentrations of the dye is 20 milligram per liter, or 20 ppm. So I use methyl orange and methylene blue as the model compounds. And it can be seen in here that by increasing the reactions times, so the colors of the dye is changing from the orange colors into the colorless. So it seems that the photocatalytic reactions appeared and the dye is successfully degraded by using the titanium dioxide and titanium trioxide mixtures. So the reaction rate constants was then determined assuming the quasi first order kinetics using the following equations, where CO is actually initial concentrations, the C is the concentrations of the dye at the T time, and the K is actually the rate constants. So it can be seen the red one is actually the anatase phase when mixed with the Ti2O3 or titanium trioxide, give the best performance compared with the rutile one. So, and also confirm that without using the catalyst, there is no degradations of the methyl orange appeared. And using these equations, this formula, in order to determine the rate constants, it seems that the mixtures which calcine at 600 degrees C or M600 exhibit the best photocatalytic performance. And when compared with the commercialized one, which is the Degussa P25, and also the parent titanium dioxide anatase, so the M600 show better photocatalytic activity by around 2 times or 2-folds. So in order to enhance the photocatalytic efficiency, I dope the M600 with the several metals such as platinum, gold, and copper. And it seems that the platinum is actually successfully deposited in the M600, but we cannot see any additional peak based on the XRD compared with the parent rutile and the anatase. So it means that the metals is successfully deposited and distributed homogeneously in the titanium dioxide Ti2O3 mixtures particles. So based on the photocatalytic efficiency in here, it can be seen that the platinum deposit in the M600 give the best photocatalytic activity compared with the M600 due to it can induce high amount of the superoxide anions, which is the reactive oxygen species, as reactive radicals, which play roles for the dye degradations. However, for the gold and copper, it actually gives the lower activity compared with the mixtures which calcine at 600 degrees C. Maybe it is due to the large particle size, or the metals is actually not homogeneously dispersed in the titanium dioxide support. So based on the stability test, it can be seen that the platinum deposited on the M600 give the better stability compared with the M600, which is actually decreased gradually by increasing the reaction cycles. So the second method is actually about hydrogenations of the titania. So it's almost the same with the previous one, but this one is using the hydrogenations or purging the samples with the hydrogens. So it can be seen that in here, the catalyst with the P25 Degussa hydrogenated at 500 degrees C give the best performance compared with other samples. So this is actually the ongoing research project about photocatalysis that will be conducted in the next following years. Yeah, about development of visible light active photocatalyst for wastewater treatment, funded by the Asahi Glass Foundations. The solar energy mediated conversions of methane to methanols, funded by Osaka Glass Foundations, and hopefully the last one, which is the long-term projects, hopefully it can be funded by the LPDP for international collaborations, but the proposal is actually still under review. So about the future outlook of the photocatalytic technology. So since in the long-term goal, photocatalytic technology will utilize sunlight, which consists of 47% of the visible light. So one of the future outlook of the photocatalytic technology is to develop the photocatalyst that is active under visible light irradiations. So among various catalysts, it can be seen in here in the pie chart. Titanium dioxide is still become the most common use catalyst, which will be modified by various strategies, yeah, non-metal, metal doping, heterojunctions, defect generations, and so on. So some of the large-scale applications using photocatalytic technology that has been established are as follows. So the SYZYGY Plasmonics developed photocatalytic chemical system. So they claim that it's actually world's highest performance. Yeah. So they actually developed which called the antenna reactor plasmonic photocatalyst. So this this result has been published in the leading academic journals such as Science, Nature, and so on. So the antenna reactor photocatalyst is actually the combinations of the larger light harvesting plasmonic nanoparticles and smaller traditional catalyst nanoparticles. And the second one is in order to solve drinking water issues worldwide, Panasonic has developed its own photocatalytic water purifications technology. So this technology uses photocatalysts and the UV rays from sunlight to detoxify polluted water at high speed, creating safe and drinkable waters. So this breakthrough is actually caught much attention, yeah, because Panasonic is actually used titanium dioxide supported with a zeolite-based catalyst and aims to provide this water to small rural communities. For example, using trucks equipped with the photocatalytic water purification systems. And in the long-term goal, they want to make the groundwater, which is polluted with several emissions, become the drinkable waters. And lastly, the Daikin developed air conditioning with photocatalytic technology for air purification. So as we know that the photocatalysis only tackles certain chemical forms of air pollution, so that in this case, for the air purifications need comprehensive integrations using the bioactive filter, plasma ionizer, electrostatic dust collection filter, photocatalytic technology, and also the streamer deodorizing catalyst. So I think Professor Yoshio Okamoto will explain in detail regarding the developments of these air conditionings using the photocatalytic technology in the next sessions. And lastly, our future outlook photocatalytic technology in Indonesia. So based on the RUEN 2017 or the National Agency General Plan, so methanol will become one of the main chemical commodity in Indonesia. So in here, the photocatalytic technology should be integrated with the other technologies such as CO2 capture, separation unit, and also product storage. So this is actually the rough schematic, in order to convert the CO2 from the flue gas to methanols as one of the important commodity in the future. So based on the techno-economic analysis, even though the price of the methanol by using the photocatalysis technology is still high, however, the photocatalysis provide the sustainable green technologies and also the safe technologies, because photocatalysis is actually conducted under ambient conditions, which is at room temperature and atmospheric pressure. So in conclusions, the photocatalysis is a promising green and sustainable technology for various applications such as wastewater treatment, air purifications, CO2 reductions into value-added chemicals, and energy conversions. The second one is a development of the visible light active photocatalyst will be the main challenge, so that the photocatalyst can be activated by the sunlight in order to conduct the reductions and oxidation reactions. And based on the techno-economic analysis from the relevant literatures, photocatalysis can be implemented in the large-scale applications. So I would like to say thank you once again to the committee for this opportunity, and I hope my presentations provides fundamental and future perspective of the photocatalytic technology. Thank you for all your kindly attentions, and feel free to ask if you have any questions in Q&A sessions. So I will return the time and place to the moderators. Thank you.
Okay, thank you, Dr. Hendra, for the wonderful presentation, especially on the fundamental of photocatalyst and recent advance in the development of photocatalyst, especially the visible active photocatalyst. We will now proceed to the second speaker, Dr. Yoshio Okamoto, Daikin Industry. Dr. Okamoto serves as the director and chairman of International Committee of the Photocatalysis Industry Association of Japan, or PIAJ. He is also a guest professor at Tohoku Bunka Gakuen University, and he received the bachelor's and master's from Osaka University and a doctor of engineering from Nihon University. Dr. Okamoto, the room is yours.
Okay, thank you very much. Okay, thank you, Chairman. Can you see my presentation display?
Yes,
okay.
Yes, the presentation is on the appeal.
Yeah, okay.
Professor.
Thank you very much. So thank you very much for inviting me in this web seminar. So today I will talk about the activity and roles of PIAJ. So my name is Okamoto from PIAJ Japan. So it's four contents in this topics. One is the introduction of PIAJ, and the second one is certification system of PIAJ. And the third topics is international standardization and some project. And the last one in Japanese market. So this is PIAJ starts the activities in 2006. So PIAJ means Photocatalysis Industry Association of Japan. So this is a logo mark. This orange line shows the sunshine, and this blue line means the water depot. So our member is three categories. One is regular member. Regular member means starts the activities of photocatalysis business, and supporting member is prepared to start the photocatalysis business and testing institute. And special member is a personal member, researcher and professors and so on. And total member in our PIAJ is 191 in this year. So this is the organization of PIJ. So chairman is Takaharu Fuji, Japan Photocatalysis Center. So he changed this year, a new chairman. And under the boarding of directors, 1, 2, 3, 4, 5 committees is activities. So I work for international committees. So PIJ purpose and every committee's activities. So PIJ's purpose is creating and expanding photocatalysis market and improvement in people's life with photocatalysis. So standardization committee's activities is to standardization of testing protocol and determine the product standard and design decision of criteria. And the standard steering committee is activity is certification and operation of labeling system. So I introduce later. And marketing committees is to attend the exhibition and propaganda photocatalysis products and research of Japanese market. And technology committees is planning and holding of technical meeting. The international committee is support standardization and cooperate with overseas organizations. So second topic is the certification system of PIJ. So we started 2006, about 14 years ago. In that stage, the customer is confused. Which do you buy photocatalysis product? Which products do we choose? So in 26, product standards are urgently needed. The product standard means confidence of photocatalytic functions. So we have to establish the product standard by 4 steps. One is testing method to determine the testing meeting according to ISO. And 2 is determine the criteria for judgment. And 3rd step is certification, check the data and performance and safety. And last in the labeling, operating labeling system and the display guideline. So we start to certification system from 2009. Now, Japanese market is photocatalysis market is stable. So this is a initiative. Test method and criteria to determine the criteria is the role of the standardization committee, and certification and labeling system the role of the standard steering committees. So our international committee to collaboration with the standard committee and discuss the ISO and JIS, the standard. So this pink area is industrial initiative. So this function for certification activities. So this is a function and test method and light source, UV light and indoor light. These are JIS number and ISO number. So colored green, self-clean, and air purifier and antibacterial is the certification functions. Especially self-cleaning is water contacting angle and methane blue decomposition. And air purification is target gas is 4 kinds of gases. And antimicrobial is antibacterial. And last year we started the antiviral certification. And now is anti-algal functions we under consideration. So this is a certification mark, this mark, PIJ mark, and registration, year, and number, and functions, for example, self-cleaning and air purifier, air purification, and antibacterial, and antiviral. So under UV lighting source condition or visible light conditions. Now is 42 companies, 107 product is certified and check the certification mark. So we think each country needs to apply certification system as a reference of Japanese system. So we think in the future, we focus mutual recognition system. So every country is to certify one product, so it's the same or common level in all Asia countries. So we focus in the future in mutual recognition systems. And third topics as international standardization activities. So we start to 2006, and every year we attend ISOTC 206 meeting. So photocatalysis is working 9. So convener is Professor Dr. Takeuchi. And 2006 to 2011, we joined the national project by NATO. So it's the development of the visible light responsive photocatalysis. So under this project, we start CAS meeting 2007. And after that, the fund is stopped. But this CAS meeting is very important. So we want to continue. So we try or restart 2013 in Tokyo, and every year we held a CAS meeting. But this year, unfortunately, the COVID-19, so we have the web meeting planning. And under the Asian countries collaboration is we have the round robin test, for example, self-test, and for example, antibacterial test. And another one is antibacterial test. So this is a new test method for antibacterial activity and simulated actual indoor lighting environment. So not in the lab test, in the actual test method. So we have the 2014 to 2015, the project round robin test and site test. After that, new proposal to ISO and published in the new ISO method. And now we start the new light source LED project because the light source is rapidly changed to LED light source. So first one is indoor white LED light source project. We started 2017. And now is new proposal stage. And last year, we started the UV LED source project. This is a 3 years project. So first one is introduced the CASP meeting briefly. The CASP meeting is a committee of Asian standardization of photocatalytic material and product. Our goal is to create a new environment industry by expanding the global market. So to obtain consensus of collaboration standards and coordination of Asia framework and round of test and ISO test methods spread to existing standard test method. And improvement of the standard concerning Asia climate and environment and joint proposal and so on. So this is a collaboration performance, especially the standard proposal. So one is antibacterial and indoor lighting environment. So this is a China and Japan joint proposal. The ISO 17094 is published 2014. And next one is antibacterial activity at the practical in actual indoor lighting environment conditions. So this ISO is 22551 is published in this year. And we start indoor white LED light source 2017. So now is committee draft 2448 in progress. And just is finished the voting and will next step CDF. And now is last year, we start UV LED light source project last year. And another one is round robin test, self-cleaning and antibacterial with Asian countries like this one. So this is a CASP meeting for group photo. CASP 2018 is the meeting is in Malaysia. So Oshi-san here and Arif-san here in the Indonesian member to attend this time. And last year to South Korea, this is group photo. And the next one is national project with Asia members. So this is an international standardization of test method of photocatalytic antibacterial performance at actual environment. So this is a scheme and 2 years project. So our PIAJ is a round robin test with Asian countries, 5 countries and Japanese 6 laboratories. And site test is in Asian country, especially in Thailand hospital and Japanese university. It's evaluated in actual environment. And KISTEC is in Japanese laboratory is activities development of new standard protocols. So before the round robin test, we have the training meeting in Kyoto in Japan. So to 5 countries expert to attend in Japan and training in like this one, the explanation and demonstration and the confirmation of test procedure and like this one to illumination meter and illumination system. After that, they proceed the round robin test in each countries. So Thailand, Malaysia, Singapore, Philippines, and Vietnam to present the result of round robin test. So we discuss at the panel discussion at the CASP meeting like this one. After the 2015, we have the site test in actual environment. So in this case, in the Thailand hospital, in this case, in Japan university. So we put the visible response photocatalytic seat put on the table. Anyone can touch every time, everything. And counter table, wash hand, and waiting here. And in the university, in the top of the desk and surface of the office. So we continue 6 months to evaluate the antibacterial performance in actual area. So this result is referred to the new ISO proposal. And third one is a new light LED project. So we start indoor light, indoor LED, a white LED project, 2017 to this year. And last year we start UV LED light source project. So 2022, this is a scheme of this project. So UV light source, for example, the difference of spectral distribution between UV fluorescent lamp and UV LED. So this green line is a BLB, black light blue spectral distribution. And this blue line is UV LED. It's very narrow band. So this UV LED lamp is just on the market. So this is a 10 tips UV LED device chips inside here. So this is a UV device. I like this one. So this is a schedule of UV project. So the target date is 2021, next year. So we propose to ISO 206 a new work item, so UV LED test protocol. So please join this project for expert and please voting the ISO voting. So last one, so we introduced in Japanese market trend. So this is the Japanese market sales amount. So from this figure, the market is gradually increased. But for 2016, before 2016, the sales amount was estimated value. But from 2017, the sales amount is the sum total of PIJ number of sales. So in 2018, the total sales number is 0.674 billion US dollars. And this is a breakdown pie chart, and about over 80% is external material, and second is internal material and amplifier and house appliance. So this application, paint, tile, and glass and tent. So this is the exterior application. So we think in Japanese domestic market from Japan to the world, especially in Asia countries, in all over the world. So this is a landmark application to the landmark symbols building. This is a tent material. So last topics in the Kirei Japan project of PIJ in domestic project. So market promotion project Kirei Japan has been started 2018. So Kirei means in Japanese. So and Kirei means clean, beautiful, and hygienical. So air purifiers is keep clean, and self-cleaning is keep beautiful, and antimicrobial is keep hygienical. So for example of constellation and products introduced with pictures and this homepage address. Sorry, but in Japanese only, I'm sorry. So this is the Kirei Japan's activities. So this technical seminar, technical meeting for members and for consumers, and bus tour to check the construction photocatalytic product. This bus tour and lab tour, and exhibition to attend the exhibition and promote in all Japanese product, photocatalysis product. And this is a Kirei Japan symbol mark. So red and white, just in Japanese flag. Oh, thank you very much. Thank you so very much attention.
Okay, thank you very much, Dr. Okamoto, for the presentation. We briefly understand what PIAJ has been doing in doing the standardization for the product. And also we have some brief insights on how the Asian countries are developing this particular technology. Of course, we would like to know more in the Q&A session. But we are now moving to the third speaker, Professor Nurul Taufikur Rahman from the Indonesian Institute of Science. Professor Nurul received his bachelor's and master's in mechanical engineering from Kagoshima University in Japan. He also received the Doctor of Engineering in Material Process Engineering from the same university. And also, he also holds another PhD degree in Business Management from Bogor Agricultural University. Is now serving as the head of Research Center for Metallurgy and Material at the Indonesian Institute of Science. So, Professor Nurul, the room is yours.
Okay, thank you. Good morning, ladies and gentlemen. It is my pleasure to be here to have an opportunity to share our experience, a little bit experience about how to commercialize our research result. Because of the limitation of in the internet, I do not use the camera. Sorry, I will off the camera. So I will try to share my presentation. I hope all of you already get my presentation. Is okay?
Yes, Professor Nurul, please proceed.
Okay, thank you. Today my topic is talk about commercialization and installation of nanotechnology in Indonesia, case study of nano team in LIPI from lab to the industry. I was between two richest millennial in Indonesia. Here is Zaki, CEO of Bukalapak, I think from ITB also, $6 billion man. And here is Dimas, CEO of Gojek. Before, I think now is already moved to another job. A $10 billion man. Both are unicorn in Southeast Asia. It seems that I smell like a $1 billion man. Okay, my talk today is about, I will divide to 4 sections. First is about innovation and technology transfer, challenge in Indonesia, technology transfer strategy in LIPI, startup incubation program in LIPI, and nano center success story. Maybe talk about my team. Jokowi now questioning the existence of scientists in Indonesia. If you are a scientist in Indonesia, you are also questioned. Where are the research output from scientists and university? This is what they are claim in the media, 2.4 billion of budget. Where is the result? If you are an Indonesian scientist, you are questioned. So take care, don't you dare to be calm. Yeah? We are now trapped in this comfort zone. Research results are only going to the library. Now our president and all stakeholders in the Indonesia are now questioning where our research output are going to. Where we are trapped again in this myth because LIPI Sciences only focus on the basic research. Don't ask them about the commercialization. They only spend their fund just to do the research. There should be another institution or agency that handles, applies research, development, and commercialization. In reality, innovation is very complex, not like this myth. Maybe all of you know that nanotechnology is basic research. However, right now, we have more than 50 products using nanoparticles from our invention already in the market. By nanotechnology, we can directly transform lab scale products to be commercialized product. For example, I can produce 1 kilogram rice nanoparticle per day on my lab for cosmetic application. Since rice nanoparticles only account for 1% of finished product, then we can produce 100 kilogram of cosmetic product, which means that we can directly jump from basic research to commercialization phase without going through applied research and development phase. In conclusion, innovation is everything that can be commercialized and useful for the society. Therefore, innovation is invention times commercialization. If no commercialization, it is just a mere invention, not an innovation. However, I think bringing research result to the society and industry is not easy. There is a long winding road to the commercialization. Bringing research output to the society and industry will face so many setbacks in the process of technology transfer, because technology transfer process is complex. Majority of scientists lack entrepreneurial spirit. No reliable mentors. Government regulation haven't fully supported, and all of us know this feeling of death of innovation. Later, I will explain our experience in detail on solving this problem. This visual shows the presentation of my college, Tim Capstel from Business School of UQ. He said that the success rate of patent is only 2%, but it increased to 9% when we make startup, and it increased to 18% when we make new product from it. Therefore, in LIPI, National Institute of Sciences, we make two pillar for increasing the amount of startup and new product numbers. Here is a IP management system in LIPI. Start with IP identification, IP information searching, analyzing, IP document drafting, and registration, and then we make some program, workshop, in-house training, patent mentoring, and so on. And also we also have technology transfer program in LIPI like this, technology transfer, I think just you can see. Then next, to measure how ready a technology is to be implemented, we use technology ready level. I think all of you already know about it. And also in LIPI, we develop in LIPI, we develop this commercialization readiness level, which is the method to validate prototype of research. If it's just an idea, it will have a level 1 CRL, and so on until level 10, where the product has a license. By using these tools for promote prototype evaluation, we can increase the commercialization level of our research output in LIPI. So next, I will join to talk about the technology transfer models in LIPI from lab to the industry. This the model 1, technology transfer model 1. Research center in LIPI giving a license directly to the user industry. Inventor did not get the sufficient right to the financial regulation in Indonesia. This, I think, not suitable. It's not going well, I think. And technology transfer model 2. In the second model, inventor will try to find an investor that will together create an industry. This is a good but bad model, I think, and bad but good model. Because after 4 years, the researcher resigned from the LIPI's position as a researcher and become an entrepreneur. Okay, good but bad, or bad but good. This PT Aneka Farmasi Indonesia, the biggest tempe yeast in the world, productivity 1,000 tons per year, supply 60% of tempe yeast in ASEAN. And model, Center for Innovation or incubator give grant for product development. They help to find industry user and give license to industry. Incubator have their sufficient in ownership, I think, with sustainability. I think this kind of example, composite filtrasi LIPI listen to PT Anugerah Mustika Agustindo. Fourth, I mean the transfer model 4, inventor and technology. This is my, I think, my preferred and the best model for public institution research like us. I think inventor and technology technopreneurs build startup in the incubator center. Incubation center giving grant for product development. Tenant together with the investor are developing the manufacturing industry. Incubation center giving license to the manufacturing industry, which is sold to the user. Inventor have their own ownership. This some example. Rice nanoparticle is by PT Gizi, and also nanobubble machine licensed by PT Nanobubble Karya Indonesia. We already licensed. It's my product. So this, I think, model is the most suitable for technology transfer from lab to industry. Next, I will try to talk about how the role of startup incubation program will help us in the valley of death of innovation. This is the first stage in the incubation program, about 1 to 2 years. The inventor have the technology. If the product have market potential, innovation center will give first seed money for developing the product sample. Then there must also be a strategic partner. I don't recommend that inventor enter this field. It can be anyone who have entrepreneurial passion that will run the business process. It must also be a second seed money for selling the product and operating the business. The output of this stage is minimum of available product, captive market, business plan, and products early adopter. So this stage will help the technology transfer from this point to this point. This 1 or 2 years. Then next, stage 2, in the second stage, at the 3rd years and beyond, the tenant startup along with inventor and so on here will be trying to find angel investor to make further step. Like in my case, the angel investor will help us about 500,000 US or $1 million US. So output of this second stage is production plan is established, business traction is growing, captive market 10% from the market incorporated. So this this stage will help the technology transfer from this point to this point. Then the third, the last stage, the startup will meet the venture capital to further expand their business, I think here. And it's like this from here to growth, and the output is IPO, I think. Last but not least, finally, I will talk about Nano Center in Indonesian activity in applying the 4th model. Okay, there is my young entrepreneurs. We have 150% now, under from 20 to 30 young people in Nano Center. And this is our team achievement. We now have already 32 patent and copyright. We have more than 300 publication, award, and many things. So we want to bring this to the marketplace. This is some of my patents, our patents, and maybe there are in many medias, top 10 national inventor by Tempo Magazine and others that we get from Habibie Award also. And we get 2 times for Habibie Award and WIPO inventor. Now we build the holding quarter in Puspitek. And here is the founder team, Dr. Ikono, Arif, Surya, and Dr. Alfian. Just co-founding partner scientists, Professor Nasihin, and many others. And so this Nano Ventures, we give operation capital, co-working space, business coaching, and we're trying to find investor and network we meet entrepreneur and scientists join together. Last year, we have 10 startup, 2.5 million US of the cumulative revenue, and we also already create more than 100 job. Yes, some our startup. You can just see revenue in last year. We also have this one, and this I will start the video.
Nanotech Herbal Indonesia merupakan perusahaan pemula atau startup company dalam bidang manufaktur yang berdiri pada bulan September 2013. Pada tahun 2014, PT Nanotech Herbal Indonesia mengikuti seleksi inkubasi teknologi di lembaga inkubator BPPT. Nano diprediksi akan jauh lebih hebat dari pendahulu. Kitosan nano dalam mengobati luka basah penderita diabetes juga menjadi hal menarik lainnya. Unit kedua adalah jasa karakterisasi bahan. Unit ini merupakan bagian dari R&D yang membantu pihak luar perusahaan untuk melakukan uji karakterisasi bahan di NHI menggunakan mesin dan alat yang dimiliki. Unit ketiga adalah jasa nanoprocessing. Dengan teknologi yang dimiliki perusahaan, Nanotech Herbal Indonesia membantu industri-industri herbal Indonesia untuk memiliki bahan herbal yang sudah diproses dengan teknologi nano.
And there's some startup for cosmetic production.
Anda masih bersama kami di CNN Indonesia Tech News. Teknologi nano diperkirakan akan menjadi teknologi masa depan. Dan kini teknologi tersebut juga sudah mulai banyak digunakan di Indonesia. Salah satunya untuk dunia kecantikan.
Produk kosmetik kini telah jauh berkembang. Teknologi nano yang biasanya dimanfaatkan pada bidang sains, kini juga diaplikasikan untuk produk kosmetik. Produk kosmetik yang mengaplikasikan teknologi nano memiliki daya serap dan perlindungan yang lebih tinggi dibandingkan produk sejenis. Nano dalam produk kecantikan wajah di Indonesia sejak tahun 2013. Ya, memang produk kecantikan yang menggunakan teknologi nano langsung terasa karena partikel yang dibuat sekecil mungkin langsung meresap ke dalam wajah dan membuat wajah lebih segar dan bersinar.
I think this is also maybe application of nano titania or nano zinc oxide. Yeah. And we also have nano bubble and also nano property, nano land startup. And I think our nano bubble startup win the competition last year, and also in incubator competition, and also win in competition of Wirausaha Mandiri, #1 based on the best.
Kami persilahkan ke atas panggung Dedi Cahyadi.
Selamat malam Indonesia. Perkenalkan, saya Dedi, CEO dan co-founder dari nanobubble.id, startup penerapan teknologi nano untuk mampu meningkatkan produktivitas budidaya perikanan di Indonesia. Pak Wendy dan Pak Nawawi di Situbondo mengalami kegagalan panen hanya 2 pekan menjelang panen itu terjadi. Dan 60% lebih masyarakat di Indonesia mengalami kegagalan panen. Maka kami dan tim membangun suatu mesin yang mampu menghasilkan gelumbung berukuran halus, nanobubble namanya. Apa dampak dari nanobubble? Pertama, oksigen meningkat signifikan. Pernah kita 2 kali lipat di Situbondo. Yang kedua, kita mampu meningkatkan produktivitas hingga 100%. Dan yang ketiga, kita meningkatkan daya tahan dari serangan virus dan penyakit. Saat ini kita mencoba mengaktifasi lahan-lahan marginal di penduduk masyarakat pesisir yang menguasai 32% kemiskinan di Indonesia. Oleh sebab itu, mari dukung nanobubble untuk membuat petani dan udang lebih bahagia. Assalamualaikum warahmatullahi wabarakatuh.
Untuk pemenang terfavorit terbanyak, ya, dengan like, comment, dan share terbanyak.
Also, we developed and implemented in Situbondo, KKP Situbondo, and many. And also we have Scoters is an online end-to-end application for abroad study, including scholarship, payment, and consultant service. We have so many product, more than 50 product based on nanotechnology is already in the market. This several the champion of the product, propolis, and it's also propolis and many things. I think using alga, I think this one spirulina. Also, maybe all of you know about this one.
Gak perlu khawatir karena kulit kusam. Gizi Essential White cerahkan wajah cantikmu.
And also this one, I think last couple years ago.
Di saat semua tidak berjalan mencegah kerutan pada wajah. Garcia Skincare, cantik dalam ketaatan.
And many things, we also make nano gold for cosmetic, and camku cholesterol herbal drinks, many things. And I see if you go to Indomaret, you may see nano silver is also our product, and new product, many things. I think now an example for using TiO2 photocatalytic, we have also some product. The attack airborne nanotechnology for anti-COVID treatment with patent number this one has been licensed to the PT Nanowabel Karya Indonesia, and also we developed masker using TiO2 nanoparticles. I hope can help society for this pandemic COVID. Last but not least, the conclusion, the key to success for technology transfer from lab to the industry is technology transfer model 4 is the most suitable framework, invention with a good potential, effective policy and program for technology transfer, entrepreneurial attitude, knowledge worker, and solid team, I think. And this last.
Saya ingin memaknai dari konteks ini bahwa membangun bangsa ini seharusnya ini peran kita sudah jelas. Mari kita otak kita ini kita agak sedikit peras lah gitu, tanda kutip ya. Masa sih kita nggak bisa mengangkat satu produk, dua produk, tiga produk yang bisa mungkin berkontribusi terhadap negara kita. Kok nemen kalau bahasa Jawanya itu kok sangat sekali. Saya yakin sih pasti bisa.
Thank you so much. This all of my presentation.
Okay, thank you very much, Professor Nurul. Death Valley of technology is a huge problem for us, so your presentation is quite insightful. So, of course, the audience would like to know more on the presentation material, the presentation topics that have been brought by our presenters. So we will now move to the question and answer session. So we already have some questions from the audience. Okay. Okay, the first question to Dr. Hendra. Photocatalysis depends on the light irradiation, and based on our understanding, the different light intensity initiates different performance. Based on your experience, how to measure the light irradiation and make sure those light was utilized to excite the electron to produce exciton. So Dr. Hendra, please.
Thank you for the questions from Mr. Huda. Yeah, so actually the light irradiations can be measured by we call it the lux meter, or also called like the illuminance meter, in order to measure the amount of light in space on a particular work surface. So in order to make sure that the light is utilized for exciting the electrons, whether it's sufficient or not. So we have to know, or based on my presentations previously, so it is necessary to know the light power, the wavelength, and also the energy, as well as the band gap of the semiconductor that you use. Yeah. So the main requirements is the light energy must be higher than the band gap energy of the semiconductors. Yeah. Further on, if the applications, for example, for wastewater treatment, so it is possible to determine the reactive oxygen species that is generated, which is the hydroxy radical or superoxide radical generations, in order to make sure that the electrons that actually excited from the valence band to conduction band is actually react with oxygens to form the superoxide radicals, or maybe the holes in the valence band is actually react with the water to form the hydroxyl radicals. So there's actually two ways in order to prove whether the light is actually sufficient to excite the electrons. Yeah. So first you have to make sure the semiconductor's band gap energy, and the second one is you can measure, for example, in the wastewater treatment applications, the radical that is generated during the photocatalysis.
Okay, thank you, Dr. Hendra. I have a little follow-up question regarding the light intensity. What about if you want to install a reactor at night, for example? How to have lights, adequate lights to activate the photocatalyst at the same intensity? Do you have any idea on that?
Okay, so my experience during my master and also during my doctoral program, so I use kind of the black box, yeah, the black box in order to prevent the light from the outside that can actually affect the photocatalyst performance, and also to make sure that the light inside the reactor is actually properly isolated. So we have to make sure that yeah, we make it in the isolation systems, so to prevent whether the light from the outside affect the photocatalytic reactions, and also the light from the inside the reactors also didn't distribute or irradiate to outside of our reactor chamber.
Thank you. The second question is from Dr. Henry Widyandari from the University of 11 Maret to Dr. Okamoto. There are two questions, apparently. The first question is, how is the synergy between academic, business, and government in the development and commercialization of photocatalyst product in Japan? And the second question, how to apply a photocatalyst to an air conditioner? So Dr. Okamoto.
Okay, thank you, Dr. Henry. So the first question is, so the government is support the new technology and development of materials. So, and in our PIJ industries is incubate and propaganda and photocatalysis product. So, so in this case, in Japanese NEDO project is development the visible light response photocatalysis material. But the industries is use that materials and develop the put on the product. So another one is it's very important to develop the standard, international standard. So government is support this standard. And next one is very important to in our PIJ to judge judgment which customers choose which product is better. Or so for that one in our certification system is very important. But this is not in industry activities, not to support the government, not to commercialize the government. So this is a collaboration with government and industries. It's very important. And in Japan and in Asia members, the collaboration is more important. So the second question is how to apply the photocatalysis in air conditioning. So about 10 or 20 years, we adapt photocatalysis to the filters, air filters. But air filter is the main function is dust collection. And another one is deodorization filters. So we decompose harmful gases. But it's very important to observe the some gases and harmful pond. So I think now is in Daikin for in Daikin situation. So we change the photocatalysis to plasma discharge unit. So because photocatalysis we adapt 10 or 20 years ago. So it's very no impact for the market. So we change our original technology plasma. We instead of the photocatalysis. I'm sorry, but now is many companies to develop the photocatalysis to air filters. It's very important. It's okay. Sorry.
I have a follow-up question regarding your explanation. So yeah, it is quite interesting that Daikin has already started in implementing or applying photocatalyst in its product several decades ago. At that time, which one actually come first? The production of the air conditioner which utilizes the photocatalyst, or the standardization, or it comes in parallel. So you are doing the standardization process at the same time with the product development.
Yeah, first we adapt the air purifiers photocatalysis, but in that day there is no standardization. So after that, especially in indoor lighting conditions is very important. So now we start the activity to develop the standardization in the environment, indoor environment. But the more important thing is that it's, I think, is a laboratory test. So it's in the share, petri shares. But if the materials, the performance is antibacterial performance is over 99, but in the actual area, it's very the performance is very low. So we checked in actual area, and I think the 50%. So according to this one, so we developed the antibacterial performance test in practical in actual areas. So it's the example for antibacterial test. So now is very interested in the COVID-19. So the antivirus test is very important. So we now trying the every virus tests. Thank you.
Okay, thank you. We have a third question to addressed to Professor Nurul from Dr. Osi Arutanti. If we are heading to commercialization of the technology, when is the right time to assess the techno economy? Professor Nurul?
Yes, okay,
Yours.
thank you. Thank you for the questions. I think there are some stage for commercialization. First, we have to know after we file the patent. I think after patent registration, I think we can just fight to find the partner to commercialize our technology, our patent. So I think for the fourth model of my presentations, we have to find a partner, maybe young entrepreneurs, our student, or many things. You can maybe you just select them, and because to assess the techno economy, you need to know how the big of the market size. Maybe first when you start doing research, maybe you know that there are so big market, but the captive market maybe you still don't know. So you need to to more detail to understand about the size, the market of size, the real market captive. So you need the partner. They develop a product, so your patent to become a product that the market needs. Then when so there is the needs they want to buy. So you know the market, the size of the market. Then you at that time you can assess the techno economy by try to produce, maybe after getting a registration patent, you still need to make a product. So you have to calculate how much money you spend to produce your technology. So you need this one also. So you need more partner, I think. We have this partner can help us to calculate, make production and calculate and to assess the techno economy. Don't use for yourself. Don't calculate by yourself the techno economy. I think the researcher never could as techno economy feasibility study of business plan. I think never become real business plan. I think is my.
We are not prepared to do that, right?
Yes, I think yes. We have to another person, another our partner, because there is so many, complex about how to assess the techno economy.
Okay. Okay, thank you, Professor Nurul, for the explanation. Yeah. So we still have some questions. Maybe the committee can help me by displaying those questions. Okay, the first question is from Mr. Ahmadi. Addressed to Dr. Hendra. What do you think about the improvement of photocatalytic performance due to the charge recombination? Dr. Hendra, please.
Okay, thank you, Mr. Ahmadi, for the questions. Yes, the charge recombination is actually one of the main issues in the photocatalytic technology, since the electron lifetime in the conduction band is actually very short, which is in the femtosecond range. Yeah. So in order to overcome this issue, so several strategies can be developed, yeah, as I mentioned in my presentations, such as doping with metals and non-metals, yeah, which are conducted in order to scavenge the electron in the conduction bands, yeah. For examples, in my research, I use platinum as a metals, so acting as the electron scavengers, which can inhibit the recombinations of electron and holes. Yeah, and other strategies that can be also conducted is actually by combining two semiconductors, photocatalysts, or we call it as the heterojunctions photocatalyst. So the electron lifetime in the conduction band will be much more longer.
In terms of the product homogeneity, which strategy is better? By doping with metals such as platinum or creating a heterojunction? In your opinion?
In my opinion, is so based on the several literatures, doping with metals will give you kind of the higher catalytic performance compared with other strategies. But actually, the main issues is the price of the metal is actually very expensive. So when we want to apply it in the large scale applications, so the cost is very expensive. Yeah. So there is actually the advantage and disadvantage for each strategist. So you have to, if you want to make the catalyst with highest catalyst efficiency, you can use the metal doping. But the consequence is actually the price is very expensive.
Okay, thank you for the explanation.
Yeah.
Okay, the second question, I will skip the second question because it comes from myself actually, so I will just put it on the last question. So the next question is from Dr. Christina, addressed to Professor Nurul. The need for research output is often be translated into a belief that every research should be applied research. I guess it refers to the statement of President Jokowi. This potentially makes us forget that we also need basic research. What is your opinion on this matter?
I think, nanotechnology is also basic research, I think. However, I do basic research actually, but I also, in my opinion, don't think all of matter, all of job doing by us. So after I find the technology patent, because research in basic research, I think, then I move it to the partner. We find the partner, entrepreneur. So they think about this, not us. We still doing basic research and develop maybe new technology, or maybe go deeply of our research. So that I propose in my presentation, we have to join with partners, young partners, especially entrepreneur who has entrepreneurship, so that they can help us to bring our research result, even basic research, to the industry. I think this of things so in my mind, in our mind, because it is the reality we live in Indonesia. I think this is my opinion.
Okay, a little more question on that. When you're looking for a partner, in what level of the technology readiness you have achieved?
Yes, so I already give the presentations from we got the patent.
Okay,
because if
patent.
we also already patent registration, so the technology can be moved from lab to industry. Okay. You see, because we got already the certificate, or maybe the patent that we believe this is intangible asset.
Yeah,
we got the asset, intangible. Yeah. So we can move this asset, our knowledge, to industry from the patent registration.
Okay, well noted, Professor Nurul. So I guess the last question to Dr. Okamoto from myself. Could you tell us more? Has there been any challenge in putting this particular technology into production in Japan, according to your experience?
Yeah, okay. So in Japanese market is about over 80% is the self-cleaning functions. So in the customer's demand is one is self-cleaning and one is antimicrobial. So, and on the other hand, over 100 products in the certified and labeled is almost the self-cleaning function. So now we start the localization of ISO test method for anti-algal performance to GS. And recently, under COVID-19, evaluation for antiviral performance is gathering attention. So we the next target is antimicrovirus. Thank you.
Okay. Okay, thank you, Dr. Okamoto, for the explanation. So, ladies and gentlemen, I guess we have come to the end of this webinar because of the time limitation. So, just to summarize from today's webinar, I guess we have a complete perspective on the development of photocatalysis and nanotechnology in general. Dr. Hendra gave us insights on how promising the photocatalytic technology is, and what stage we are in, what are the challenges that we have in developing the technology in terms of lab scale. Professor Nurul, we learned that a partnership is very important if you want to survive the death valley of technology. If you want to develop technology, including nanotechnology, partnership is very important to survive the death valley. We are often trapped in the death valley, so that's why it is difficult to implement or to commercialize any technology in Indonesia. And from Dr. Okamoto, emphasizes the needs of standardization, not only about the product, but also about the lab test, because this is the process, this is the core process of the product development, and we need standardization, not only in the products, but also in the lab. laboratory testing. I would like to thank you, thank the speakers. I believe that what you have shared today will contribute highly to the development of the catalyst in Indonesia and also in the development of technology in Indonesia. So thank you very much for your contribution. So I would like to return the room back to the Master of Ceremony.
Okay, thank you very much to Mr. Arif and all the distinguished speakers. That was an interesting talk. I hope it can give us new insights about photocatalytic technology and can be implemented to advance our industry. Ladies and gentlemen, before closing the event, I will give you some important announcement. One, for those who have registered in this webinar session, please fill in the attendance list on the link provided in the chat room, both in Zoom and YouTube, for the purposes of sending e-certificates. Two, the 2020 STKSR-Symphosis main event will be held virtually on November 16 to 17, 2020. And the last one is all information related to 2020 STKSR-Symphosis activities can be seen on the website stksr.che.itb.ac.id. Ladies and gentlemen, now we have come to the end of this event. On behalf of 2020 STKSR-Symphosis Committee, I would like to express my utmost gratitude to all those who have supported this event and to the all distinguished speakers and webinar participants for your kind attendance and active engagement in the STKSR webinar series pre-event. I would like to also apologize for any inconvenience throughout the event. Once again, thank you and see you at the main event of 2020 STKSR-Symphosis virtual conference. Bye-bye.
Bye-bye. Thank you so much.
Thank you so much.
Thank you so much.
Thank you,